Dr. A here, and in this video we're going to be providing some background information on internal loading functions. So let's go ahead and get started. It turns out that we can derive internal loading functions in a member by using the method of sections and making a cut at a variable location x from a defined origin, okay? So what have we done so far? Well, most of what we've done so far with method of sections and internal loading in beams, for example, is that we have made a cut section using method of sections at a specific point. Like, for example, we've seen examples where we say use method of sections to figure out the internal loadings at point B, and point B is 3 meters away from point A. So we know in those previous examples that we're making a cut at a specific point that is a finite distance away from an established origin or reference point, okay? Well, here what we're talking about is developing actual mathematical functions. So you could have shear as a function of location x or moment as a function of variable location x instead of finding the specific shear and moment at a point that's just a number, okay? So how do we do that? Well, we follow the same process we did before, with the exception of we need to clearly define an origin. So let's look at this illustration here. Here I have this simply supported beam. I have a support of an external pin at the left and a roller at the right. And I've put this little origin here. In fact, I can go ahead and label that as point O for origin. And I've said, okay, I'm going to have this location variable that I'm calling x pointing to the right, okay? And so when we do method of sections, what we can do now is we can make a cut at some general arbitrary distance of x away from the origin. And then once we open up that cut section and we have those internal loads, they're going to be based on that variable location x instead of an actual finite distance or number that's in feet or meters, for example, okay? Now, here are a couple things we have to keep in mind that, is a little bit more involved with internal loading functions. The first thing I want us to keep in mind is that if we want internal load functions for the entire beam, we need to make a new cut after every time there is an abrupt change in loading on the member. And most of the time, and for our purposes, when we say member, we mean a beam, okay? So for example, if we have a member like this, okay, and let's say that, let's say it's pretty much the same kind of beam we just saw. Let's say we have an AY and an AX, and we make this the origin, and there's our location variable X. If we have a force here, P1, and another force here, P2, and then maybe, we have this BY right here. If we wanted the loading functions, specifically shear and moment functions for this entire beam, we're going to have to do method of sections how many times? Think about it. We would have to make 3 different arbitrary cuts. We'd have to make one cut between the origin and P1, and then separately make another cut between P1 and P2, and last make a third cut between P2 and B. And the reason is because every one of these applied forces, P1 and P2, represents a change in something. So what we're going to end up getting is 3 sets of functions, and they're going to represent piecewise functions in mathematics. Okay, so for example, if we continue this illustration on our next page, what I would do is something like this. I would say cut 1, all right? And, you know, I've got whatever that AY and AX came out to be at the beginning. And then I would make a cut here. And then what becomes visible here? Well, you would have the shear force as a function of X. You would have the bending moment as a function of X. And technically, you would also have the normal force as a function of X. Although for beams, most of the time, we're dealing with shear and moment. But I'm going to put the normal force as a function of X for the sake of completeness. Now, what is this distance right here? Well, this distance is a distance X, okay? And remember, our origin is right here, and we're measuring X to the right as positive. So what we're going to have here is something like this. We're going to have n as a function of X equals some polynomial. Usually these are polynomials. Shear as a function of X is some function. M as a function of X is some function. And then what is the domain? We're going to have a domain here, which is where these functions are valid for. So what X values are these functions valid for? Well, this would be valid for example, X equals 0, and then up to whatever the location of P1 is, okay? In fact, it's that one is non-inclusive, so let me edit that just a little bit. This one is just less than, up to the point, the location, the X value where P1 is. Remember, we had this P1 over here. So basically what you're saying is if you make a cut anywhere between the origin and just up to, but to the left of P1, then these values will be valid, okay? Now, keeping with the same illustration, let's say we keep going and we have a cut 2, okay? So I'm going to draw a free body diagram again, and I'm going to have, you know, that AY and AX is still there. Well, now I'm making a cut somewhere to the right of P1, okay? And where is my cut going to be? Well, it's going to be here. Here's that X value. And again, here's my origin, okay? And so I'm making this cut somewhere to the right of P1, but not as far as P2, okay? And so what becomes visible here, well, again, we have a shear force, a normal force function, and a moment function. And I'm going to end up with another set of n as a function of X, V as a function of X, and M as a function of X. And what's the domain on for this cut? Well, that's going to be the domain is going to be the location of P1 less than or equal to X less than the location of P2. Okay, so again, going back to the original illustration here, that means I'm making cuts somewhere in between. I could make a cut at any distance in between P1 and P2. Any distance X in between P1 and P2. Okay, so past P1, but just before we get to P2. All right, and again, I get this second set of load functions. All right, and then finally, what am I going to have? I'm going to have a third cut in this particular illustration. And where's that third cut going to show up? Well, that's going to be, you know, past P2. So I've got P1 here. I've got P2 here. You know, I've got this AY. I've got this AX. I've got that location variable X there. And so this distance, try to color coordinate for us. This distance right here is X, okay? And so sure enough, again, at this cut, I've got another, V is a function of X, N is a function of X, and M is a function of X. And I've got another set of those three functions. N is a function of X, V is a function of X, and M is a function of X. And what is the domain of this cut? What's this domain? Well, again, this is going to be in between the location of P2 less than or equal to X less than the location of that point B. Okay, so looking back at our overall free body diagram, I'm making cuts somewhere here, anywhere in here at some distance X. Okay, at some distance X in between P2 and B, and I'm getting those load functions there. So what do I have here? I've gotten, in this particular illustration, I've gotten 3 sets of load functions, okay? Now, these represent piecewise functions. So, for example, what I'll end up having is like N as a function of X, and I'll have, the load function for the first domain, domain 1, and then I'll have the load function for domain 2 and the load function for domain 3, okay? Similarly, I'll have the shear function as a function of X, V is a function of X for, I'm going to say just D1 for domain 1, V is a function of X for domain 2, and V is a function of X for domain 3. And then finally, I'll have the moment function as a function of X. So I'll have those 3 moment functions, each one for each of those 3 domains or each of those 3 cuts that I made. So here we have, in math, we call that a piecewise function. So we have the normal force piecewise function, the shear force piecewise function, and the bending moment piecewise function. Now, how many cuts do we make? Again, we're going to go back. We make a cut after every time there's an abrupt change. So back on our original very first illustration, how many cuts would we need to make to write the loading functions for this entire beam? Well, this one would also be 3, right? You have a domain from the origin up until we hit this distributed load. So that's domain 1. And then you're going to have another domain from the distributed load. So this will be domain 2. And then you'll have this third domain from this last segment, domain 3. So even in this original illustration that we started the video with, we would need 3 cuts, okay? Now this can get complicated pretty quickly, okay? So like in a statics course, we introduce this concept, and then we really dive into it more in like a mechanics of materials or a structural analysis course, but we want to introduce this for sure in statics, okay? So that concludes this background video. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.